No. Are video games a good or a bad influence, independently of the age? Many researchers have tried to prove the benefits of playing video games, showing that we owe them the same respect that we owe to activities that have the potential to sharpen our perceptions and responses to the world. Based in Piaget's theories, the educational value of games has always been connected to cognitive skills development, memory formation, spatial navigation, strategic thinking, fine motor skills, attention, language development. Let's focus on what scientists and academics have said after their 1,000 studies have focused on the brain and evidences through MRIs. As anyone has explained these investigations visually, we are going to start explaining the effects and evidences, but understanding the brain first. So what exactly is the brain? Our brain is formed by 3 brains: the midbrain, hindbrain, and forebrain. The midbrain is formed by the brainstem, and it is the one that connects our body through the spinal cord, which passes with the other 2 brains. It is involved in the sleep-wake cycle, heartbeat, attention, temperature regulation, vision, hearing, blood pressure, and motor control muscles in the face and neck. It is also in charge of the more basic actions for surviving, such as breathing and swallowing. The hindbrain, or cerebellum, contains 70 million of neurons, 5 times as many neurons as physically larger cerebral cortex. The cerebellum, honouring our most practiced talents, helps to improve our motor skills by detecting errors in movement and making minute adjustments to the next movement. These procedural memories of learned motor skills can persist even when memories of events are disrupted by damage to the hippocampus. It is therefore responsible for having control of the fine muscles, having the coordination of movement, posture, balance, and equilibrium. There is also the cortex, which is formed by 4 lobes. The first one is the occipital. The occipital lobe decodes visual signals. The visual information arrives from the eye via the thalamus. While the retina detects colours, edges, and movements in our field of vision, the occipital lobe tells us where is the fork, how we should react to it, even if it is flying at our face, and helps us to recognise that it is a fork. This information is relayed to the rest of the lobes. It will go to the parietal lobe if it has to determine a response based on motion, or the temporal lobe if it has to recognise objects. The parietal lobe interprets our sense of touch, integrating things from our senses to focus our attention on important things in the environment. It receives information from the previous lobe, occipital, that reflects the location of objects. It reconciles with touch and body positions to paint a realistic picture of our surroundings. The left and right halves received information coming from the opposite side of our body. Temporal. The temporal lobe houses memories, emotions, and language comprehension, spoken and written, linking words to their semantic meaning. It is also key for the recognition of objects, places, and people. The temporal lobe contains the limbic system, and with it the hippocampus is a key part where the creation of memories takes part. We will talk about this a bit later on. The frontal lobe. The frontal cortex concedes us executive function, or the ability of making complex and socially mindful decisions, providing us with a working memory which keeps relevant information available for a short period of time in order to make those decisions. It makes sense of what the temporal lobe houses, memories, emotions, and the environment, and filters out unimportant sensations by focusing on the task at hand and contextualizing our decision with past memories and predictions about how our behaviour will affect our future. For example, an incognita of a silhouette, we filter our memories. Is it a fish because of the tail? No, exactly. Is it a basketball court? Not exactly. Is it a woman? Neither. I saw it in a Disney movie? I know now. It is a mermaid, focusing on what we have to sort out in our present moment. This lobe is the one that makes humans' behaviour and personality unique. For years, scientists and academics have been researching the benefits that we can achieve by playing video games. They've done this by gathering evidences mainly through magnetic resonance imaging scanners, also known as MRIs, of the brain. Through these scanners, it's possible to appreciate which zones are activated, and therefore where there is an improvement, such as grey matter. Action video games can increase grey matter volume. These are the connections that are made amongst the different parts of our brain and enhance functional connectivity, leading the facilitation and enhancement of neuroplasticity, the capacity of filtering unnecessary information. Learning and practicing challenging skills, our brains can remain in better shape and even grow, reducing cognitive decline, which is usually associated with aging. This helps to keep active the 86 billion of neurons that are part of our brain. These cognitive tasks are made up of spatial perception, perceptual discrimination, visual search, recall, and recognition. It is known that people that play video games are more likely to develop new brain cells and have an increased connectivity between different brain regions. This is usually associated with memory formation, spatial navigation, fine motor skills, attention, and language development.
Alright, so how many first aid kits do I have?
In 2015, action video games, known as Halo or Call of Duty, were defended for helping people to think differently.
People are going to be saying, oh, you missed it. Get over it.
Making out-of-the-box decisions and improving the speed of problem solving.
Oh, you scared? Huh? You scared? Yeah, I would be too.
This is called probabilistic inference, which is the manner of our brain works, reconnecting, rewiring, and using already stored information in order to make a fast and correct decision.
Yeah, get drilled, buddy, get drilled. Yeah, how's that feel? That work? Did that count? Please tell me that counted.
But if they are so beneficial, how is it possible to find these kind of news?
It didn't count.
One more for the bed.
In our morning rounds, video games and your kids, 90s violent content. Well, a new study finds a link between violent games and aggressive behavior in children. Dr. Harold Koplowitz is a child psychiatrist and president of the Child Mind Institute and joins us at the table. Hello, Harold Koplowitz.
Good morning.
I mean, we have so much violence on television now. How is that any different than playing a violent video game?
I think there's a very big difference. It's almost a virtual reality kind of experience, and it's very different than when my kids were playing games. I mean, my kids are 25 to 30, and if you remember, like Pac-Man, you know, bing, bing, you know, you could get so bored so quickly. But today, it's a very engaging, interactive experience, and that's what we have to be concerned about, because you're exposing kids to potentially very inappropriate material and also very aggressive material.
How is it possible to find expert players doing such activities? How can it be related to video games? How can we explain the correlation? Is it interlinked? So where is this link? Video games have been shown to benefit certain cognitive systems in the brain, mainly related to visual attention and short-term memory, said West. But there is also behavioural evidence that there might be a cost to that, in terms of the impact on the hippocampus. So what is the cost? The grey matter are the connections that your brain makes, and when it reaches and depletes the hippocampus, there is a risk of developing brain illnesses such as depression, Alzheimer's, PTSD, and schizophrenia. In 2017, a new article revolutionized what was popular about video games' benefits, arguing that a difference of grey matter volume when playing different genres of video games. The 4 years neuroimaging studio conducted by 2 Montreal researchers, West and McGill, gave evidence of grey matter reduction when playing direct interaction like shooting games such as Call of Duty, Medal of Honor, and Borderlands. The subjects tend to lose grey matter in the hippocampus. In addition, 85% of the players relied on the reward pathway, caudate nucleus, which is responsible for forming new habits and behaviours. The reward pathway. How does the reward pathway work? Let's take an example and try to remember a time when you received or did something you liked, like receiving a smile or a stroke or a gift, or eating that delicious treat. Well, in any of those situations, your brain is responding in a particular way, and it makes it feel rewarded. Pretend this is a slice of your brain, and you are looking at the right hemisphere. Now, we are going to focus on very specific parts of the brain when you first experience pleasure. When you experience pleasure by any kind of stimulus, your brain releases a neurotransmitter called dopamine. Somewhere over here, so in the middle brain, part of the brain stream is the VTA or ventral tegmental area where dopamine is mainly produced. This dopamine is sent by the VTA to lots of different parts in the reward circuit, and one of those is the amygdala. This is situated in the limbic system and is responsible for processing emotions. Another place where the VTA sends dopamine is the nucleus accumbens in the basal ganglia. This nucleus accumbens controls your body motor functions. It is also central to the prefrontal cortex, which helps focus attention and planning. The last place where dopamine is sent through the reward pathway is the hippocampus. This is responsible for the formation of memories and is situated close to the amygdala in the limbic system, forming part of the temporal lobe. So what happens then when the VTA sends dopamine to all these places? Basically, your brain says, "This feels great, let's do it again." This is a natural response for the most of the pleasure stimuluses, such as food, social interactions, affection, sports, etc. But also for artificial stimuluses such as drugs, shopping, or watching TV can initiate this response. The reward pathway that we want to talk about is the mesolimbic pathway. This includes the nucleus accumbens, amygdala, and hippocampus. We want to highlight how the reward pathway works, so we won't break down into further details. When dopamine is sent to these different areas, the response of our body is happiness and euphoria. The amygdala is a pleasurable sensation. The hippocampus will remember everything about these environments so that this behaviour can be repeated again. For example, it makes us think about where I was, with who, what time, when, and if, for example, if it was about food. What meal, how was it cooked? Or if it was music, which song, which bit, how was it played? The nucleus accumbens responsible for the motor functions will do what is needed to obtain it. If it was a meal, we'll take the fork again to eat it. If it was music, let's stand up and dance as I did before. But it can also be perhaps the accelerator of the car or shooting a gun. And the prefrontal cortex helps us to focus on that particular thing. The music, the food, the loved person, drug, offers in the supermarket, lines on the ground. For example, if a person has OCD, and then you do it again. Dance, eat, whatever it is. And the reward circuit experiment causes euphoria again, which sends dopamine, making the reward pathway stronger and experiencing a longer state of happiness. But another point in this circuit is the level of serotonin in charge of the situation. Curiously, when dopamine goes up, the serotonin goes down. This is a natural driven process, but it is here where we can enter in a dangerous loop of addiction for feeling ourselves in a state of satisfaction that doesn't last long enough. In other words, whilst the spatial memory method helps to increase grey matter, memorizing methods reduce it. First-person action games were the only types of games that sometimes led to grey matter reductions. When participants played 3D platformer games like Super Mario 64 as opposed to first-person shooters, their grey matter increased regardless of how they navigated. First-person shooting games doesn't involve spatial memory strategies. That is why the grey matter will be reduced as much as we train those type of games. In these games, we will be training just stimulus reactions without second thoughts about the environment, past experiences, or possible consequences of our behaviour in future. An example of this is an answer reaction movement in the knee-jerk reflex, patellar reflex. Another example can be boxing. A boxer, it's training in repetition to send a jack after the trainer touches his shoulder. Once the boxer goes home, any member of the family touches his shoulder, and the learned answer that he was practicing is to send a jack. It can happen. The boxer has been training that answer to make it natural and fluid, but the experience and memory stop him from answering in the same way that he would in the ring or the gym. Remember that an athlete is trained physically and mentally for guaranteeing a successful performance. We shouldn't cherry pick certain things that makes us happy and be coherent with our overview development.